quite an amazing thing to see, really. I'm not sure why it's all that relevant to this class, but the F equals ma. It's transit through the atmosphere is controlled by drag, of course, which we haven't talked about yet. We've talked about only inviscid fluids, fluids that have no viscosity and therefore no drag. But I guess it will have pressure drag, pushing against something to move air out of its way and around it. And so that's a form of drag at very high velocities. And yeah. So a big one in Siberia in the early 1900s that leveled a whole bunch of forests in northern Russia as well. I'm not sure why Russia is attracting them so often. And of course, they're just about to announce another mission to whatever the asteroid was that they crashed a satellite into to see if they could alter its path by the momentum exchange. So yeah, all part of this class in some respects in terms of the mechanics of these things. What else? The more fluid things. Oh yeah, this is a fluid thing. This is kind of the object of what we'll talk about today. A Pelton wheel, apparently available in Canada and probably the UK, I guess, from the language that was there, is a Pelton wheel. And these are used in hydroelectric plants, but this is obviously a model. You see a whole bunch of cups. If we start, does it start up? You see a whole bunch of cups that are cupped on the bottom, I guess. And so the jet of air on this thing on the left-hand side is just pushing on it. And it turns the momentum of the jet of air into a rotational momentum, which of course can be hooked up to a generator. And so Pelton wheels are some of the wheels that are used in hydroelectric plants. They're not as efficient as regular turbines, which would be more similar to jet engines, but with flow through them. But they do, they're just like water wheels, essentially water wheels, an undershot water wheel. So water wheels can be overshoot or undershot. And so overshoot means it comes across the top and pulls it down. Undershoot means it goes at the base and pushes it. And so we'll talk about that today, actually. That's kind of the object of what we want to talk about. Seen this, of course, many times, the old jet lev. And that is related to what we're discussing as well. Last week, week 6, we were talking about conservation of mass. We entertained 85 ways to calculate mass rate in minus mass rate out equals mass rate accumulation in static and moving and deforming coordinate systems. And we'll use a bit of that today, maybe, because, of course, we did this calculation with Bernoulli to see what it would take to lift a 100-kilogram person, what kind of flow rate you'd need to do that. And we used Bernoulli to do that. But I guess we didn't address one question would be, what kind of force do you need to do to levitate at some particular velocity? And so that's a bit beyond Bernoulli, although I think actually we can do it with Bernoulli, and perhaps we'll do a very quick example with that today. So these are the kinds of things that maybe we'd like to address in this. The sleeping giant, of course. This is always fun to look at.
High-pressure gas cylinders have been around for 100 years, and legends of their destructive potential have been around for 99. But could a ruptured tank really burrow through a brick wall?
Good question. What's the answer?
There we go, shearing the regulator off the tank. Attempt number 2.
We've got a guillotine, I guess.
5, 4, cross your fingers, 3, 2, 1. Yeah! That's the sound! That is a lovely, lovely sound.
The valve has sheared clean off, and that's a very good sign. It looks like the cylinder flew straight and true, but did it have enough thrust to crack the wall?
Oh, God.
It was did it.
Lard. They must put lard on the grease the skids, literally.
The air tank turned the cinder block to cinders. It even put a fair dent in the wall 6 feet behind it.
Totally.
Yeah.
I mean, it didn't go all the way through, but it went through this one and it was going. It's working its way through that one.
The so-called sleeping giant, why you are always required to tether a cylinder to a leg of a table, and always when you're moving them, you put this cover on them so that if they do fall over, they don't do something like that. And so what else have we got? Now, this is a bit boring, but let's do it anyway. You can imagine doing the same thing with a propane torch, just the opposite. Nothing inside the thing, but being shot off because of the force behind what's going on. So all exchanges of momentum between individual components. Is there another one? I'm not sure what the other ones are. Oh yeah, that's good. And I'll do this one as well. So this is actually an undershot weir. We talked about an undershot Pelton wheel. But this, we talked about weirs, the idea that you could have an upstream measured height and a downstream measured height and use that to calculate velocities with no moving parts. And so this is just an example of that. You can see it has erosion underneath it. And again, actually that's one of the examples that maybe we'll get around to dealing with today. So we can look at that. So what we're talking about today is we're moving on from talking about conservation of mass, which was kind of maybe overkill, I'm not sure. We spent a lot of time, well, we spent two periods doing it. We talked about reference frames and the substantial derivative first on Monday. And then we talked about conservation of mass as mass in equals mass out using Reynolds transport theorem last time. And so we said that we'd use that 2 more times to be able to talk about conservation of energy in a couple of different ways. Conservation of momentum and conservation of energy, as in kinetic energy. And so that's what we'll maybe do today. I always thought that we could never use, it's more convenient to use than Bernoulli. We've said before that when we're talking about Bernoulli, we're looking merely at F equals ma. And so one example of looking at that, which is actually related to the Pelton wheel, let's do that just for the heck of it, before we recap everything. Actually, perhaps I'll go a bit further down and do a thought problem. And so the thought problem is a streamline for flow between upstream and downstream. You've seen this many times. Location 1 and location 2. And as a twist, let's put a little sled in front of this, which this streamline is impinging on. And we'll put that sled on rollers so it can move. And it can move at some velocity. And we'll call that the velocity of the control surface. So if this is a jet of water, the jet of air in the Pelton wheel example, we could write Bernoulli for that equation as P1 over unit weight plus V1 squared over 2G is equal to P2 over unit weight of the fluid plus a velocity squared over 2G. But let's make this velocity. So we did the example for the truck on SFO apron being blown off into the bay. And we talked about what the force would be on this. We know that the pressure upstream, because pressures act in all directions, and it's coming out, it's in the air. We don't know what this pressure is. We know that this is a static velocity because it's coming out of the fire hose. But instead of having this truck static, let's have it moving at the velocity of the control surface. And so if we do that, we can rearrange this. We'd like to be able to figure out what the pressure is that's acting. So the pressure on the sled divided by the unit weight is equal to 1 over 2g v1 squared minus v control volume squared. We could multiply both sides by rho g, in which case we get rid of this. And we could multiply by the area of the sled. I guess the area of the sled would be this, multiplied by A. And so this now is a force that we'd have to apply to keep this static, which is just P2 times A. And we have it in terms of some things on this side. We can get rid of the G's, I guess. And so we'd have that the force is equal to an area, a density over 2. Let's multiply by V1 squared over V1 squared. Check my math. You know how won't use an expletive. How poor my math sometimes is. And so we have this expression. So you can imagine two bounding values for this. Hopefully it works out to be the right magnitudes. So let's choose to prescribe a velocity of the control surface and calculate what the magnitude of F would be. So if the velocity of control surface is 0, we're holding it. It's not moving. Velocity of control surface is 0. This is then the force is equal to A rho over 2 V1 squared. And this is the static velocity coming out of the jet. The maximum velocity this is coming out at, so this is coming out at V1. So if this jet of water is just hitting the sled and moving ahead of it, the maximum velocity it can, you could rationalize, is going at V1. And so if we take the velocity of the control surface and release it, not holding the force to keep it moving, if this is V1, then this becomes 1 minus 1, which is 0, and then the force is equal to 0. Makes sense, right? It's free to go, frictionless base. It's moving just at the tip of the jet as it's going down the lane. And I guess we could have a half V, V over 2, V1 over 2. And that would be, this would be, V1 would be a half, B2, is that right? So this is control volume. It would be equal to half. So a half squared is 1 minus quarter. So it would be equal to this term above here times 1 minus 1 over 4. 1 over 2 squared, right? And so that's interesting. It's interesting primarily because this is the way that we transfer power. So you transfer it from water into kinetic energy through momentum. And of course, if you want to look at the power you'd make from this, this is of course a simplified. You could imagine this, I suppose, being on a radius, and this being the fulcrum, and this just going around. So bang, bang, bang. Every single time the jet comes, it hits another one of these little cups, and it keeps on moving. So it's just like the Pelton wheel we just saw. Must be someone's name. Who must have invented it. And so the importance of this is that if we plot, for instance, the velocity of the control surface versus the velocity of the control surface, then that's going to be a pretty easy graph to draw, 1-to-1. If we plot the force that's acting relative to the velocity of the control surface, then when the velocity is equal to 0, it's a maximum. When the velocity is equal to V1, which is also equal to VCS, then it's minimum. And, well, it's actually not a straight line, is it? Because this was, if this is 1 and this is 0, then we also had 3/4, right, as one of our terms. So this is V1 over 2. This is V1. This is 0. And this is 3/4. Right? 1 minus 4. And so if I draw that, see how well I can draw it. See if I can use my... No. Sometimes it likes to draw a curve, but not today. Right. So I'll just draw... It's a continuous line, but it's going to look something like this. And the punchline, of course, in all of this is that we know that so work is equal to force times displacement. Power is the rate of doing work. Work over seconds, which is equal to force times velocity. In this particular case, the velocity would be VCS. So it's important because if we plot work, which would be, this is in watts, this is in joules, Newton meters per second, which are watts, after Mr. Watt. So the product of velocity and force, if one of these terms is 0, then it's 0. The product of velocity and force, if one of these terms is 0, it's 0. And so the form of this curve is going to look something like that. Oh, it did do it. And so it makes the point that if you're pushing this vane, but there's no resistance, it's happy to do it, and it will go at the maximum velocity, and that will be the velocity of the jet, but it will generate no power. You can't use it to work. It won't generate any power for you. If you hold it static, then you're not generating any work either. You're just pushing against it. To do work, you have to attach something to it that is a load on it, and that would give you the maximum amount of work for this machine at this intermediate point, which I think is kind of cool. Yeah. And so you can imagine what would happen if you attached the Pelton wheel up to an electric drill and ran the electric drill with the Pelton wheel in reverse and took current off it, then that would be a small generator that you'd have. Okay, so that gives us perhaps a reason to do what we're doing. So I've never used that before. I always thought that Bernoulli we couldn't really use very easily to make this case, but you can. All we've done is we've said that this velocity, of course, the water coming in here, if the thing is static, you could imagine that it would just shoot up here. And of course, velocity is a quantity that has both direction and magnitude. So this would be coming in at some speed, and it would go up here at some speed. The speed here would be the same as this speed, but the velocity here would go to 0 in the direction that it's going, because it's changing its direction, not its speed, right? So a good point to remember is that velocity is a vectoral quantity that has both speed and direction. And so we'll use that actually starting today. Okay. So anyway, so I thought that was a useful thing to maybe introduce our topic for today. So if we recap the things that we learned last time, it's probably useful always to do that. I think there were two things. Mainly that we could get a control volume which was largely like a streamline, could be like a streamline, stream tube. And we could define behaviors relative to that velocities coming out of it. Then we draw the outward normals in black, same color we used last time. If velocities were coming out of this as V2 and V1 going into it, then and we have X and Y coordinate systems, X and Z perhaps. And if we put units on this, then this velocity V1 is in the positive X direction, so it would be positive. This velocity v2 is in the positive x direction, it's v2. The dot product of these, v1 dot n, would be negative because it's going in the opposite direction to the unit normal. Vector, the dot product is 180, cosine 180 degrees. And this one here would be v2 dot n. This would be positive because it's arranged in the direction of this. Today, we'll also entertain the prospect that we can have a quantity which is the velocity 1 times the dot product and velocity 2 times the dot product. It's a bit premature now, but this is going to be the velocity in the Cartesian direction. So this is in the positive x, so this would be a positive value. I should have left myself a bit of space. This one is going to be negative as it was above, and so the net value of this will be negative. This value here from before is positive, all I'm doing, but this velocity in the 2 is also positive because it's in the positive coordinate direction. And so we have to be mindful of the signs of these when we put them together. We're not there yet because I haven't told you why we're doing that, but we will come back to define that. And the other thing that we talked about was static and moving coordinate directions. I love the shape of this boat. Don't you just love it? Cabin on the top. And so we did two things. We said, one, that this boat can move at the velocity of the control surface. And we also had it that if it's squirting water out here at some rate w, then those two magnitudes are additive. And so relative, we've already used this morning actually, haven't we? This is the velocity to a static observer. Static observer sees the boat moving at 1 meter a second, the jet coming out of it at 10. Relative to the observer, it's moving at 11 meters a second, which is just the sum of those two. So we kind of moved that today, used that today. We used the velocity of the control surface to be the velocity at which the water coming to point 2 was just getting to this control surface. If the control surface was moving at the same speed as the jet, then it never touched it and it never made a force. And so, and if it was static, the maximum force, the velocity of the control, we could get, right? Velocity of the control surface is equal to velocity static minus velocity, minus W. We were getting the velocity control surface, and then static velocity. If there's no water coming out of the thing, then it was the velocity of the static motion. If this was moving at the velocity of the control surface, then this ejection of water had to be 0. It was absorbed in the motion. So we said that we were going to look at conservation equations, and we defined them in terms of this extensive property and an intensive property, which was equal to the extensive property divided by a mass, per unit mass. And our first was conservation of mass. And so this was m. This was m over m equals 1. And these were the quantities that we placed in here. And so we took this as 0 because we're going to look at steady state. We took this as equal to 1. And we took this as equal to 1. And if we did that, we ended up with this simplified relationship. Rates of change of accumulation due to a changing density going into a closed volume, or an unchanging density going into an expanding volume. So either filling up a tire and the density changes, or filling up a bucket and the volume changes, and equal to the product of density, velocity, and area. So this is momentum. This is not momentum. This is just a mass rate. So area times the velocity is meters cubed per second, multiplied by density, which is kilograms per meters cubed, gives you units for this of kilograms per second, which make it up. So that was then, but this is now. So today we will talk about momentum. And that is this. Momentum divided through by unit mass is just going to give you a velocity. Not a volume, but a velocity. I guess it also serves us to remember, I should survive the class, but maybe not, is that this is a vectoral quantity, x, y, and z. Mass rate of flow, because we take the normal to the boundary, it just becomes a scalar value. It's the amount of stuff going across a boundary, normal to that boundary. There is only one direction across the boundary, so it's a scalar. But when we deal with momentum, we're solving Newton's law in x, y, and z, and so we have to be mindful of that. And so what we would do, let's see how fancy I can be here, is if we make those substitutions. So I'm going to make those substitutions. So if we make the substitutions in here, up into that same top equation, then B is going to be equal to, I'll put an underbar under it because it's a vector. This is going to be a velocity, again, and this is going to be a velocity. Bless you. And so maybe you can see why we did this, just as a little excursion, because now no longer this is 1, but this is going to be a pre-multiplied by a velocity. We'll only look at steady state. Steady state for flows. So if steady state for flows are 0, then I'm going to make that term equal to 0. No change with time of this. But we will keep this because this is important to us. It's important to us because if you remember Newton's second law, it is equal to mass d, well, let's write it as it was written there. It's rate of change in the substantial derivative, mass times velocity, divided by dt. Rate of change with time. This is just Newton's second law. We probably usually write it F equals ma. But we know we're better off writing it in this coordinate frame because this is the one that's important to us. And so if you look at this, then this term here is just equal to force. And force is going to be equal to this term on the back end. And if we write that out in simple form, it's going to look something like this. F is equal to, bless you, rho v dot n and area. That's a bad sigma. These are summations of all the components. And I suppose I should also note that this is true, right? This is a vector. And so if we write that out in longhand, it's not particularly scary. It just says that the force in the x direction, force the y direction, force in the z direction, is equal to, I guess, density Vx, Vy, Vz. And actually that's not, yeah, times V dot N A, which is probably a little easier to write in the way that we'll write it, which is sum of forces is equal to device battery is low times V. So this is a vector, has 3 components. This is a vector, has 3 components. And the density times the dot product times the area, these terms together are just the mass flow rate, the same as we had here. So we spent all last period skinning a cat 10 different ways to do conservation of mass. This was the way that we wrote this, and so this term here, this whole term here that I'm underlining is just the mass flow rate, m dot. Density, so velocity, and an area. Velocity times area is meters cubed per second. Density is kilograms per meter cubed, so meter cubed per second times kilogram per meter cubed is just kilograms per second. So a change of mass with time. That's all it is. And so that's it. So let's do a quick example to deal with that. Do I have enough space underneath here? Possibly not. I'm going to start on a clean sheet. So this is an example that's in my notes, my horrible notes. Don't know if they're horrible or not. Perhaps they're not fantastic. But it's the example so this is this example here, just an undershot weir. And so it's easier just to do it by hand. So the stuff that we've done here is the derivations. We don't need them. I think you have everything you need in this simple single equation that I'll rewrite here. So momentum. And that is that sum of forces are equal to sum of velocities times mass flow rates. The underlined ones are vectors, which are x, y, and z. And I suppose actually it's useful for us to maybe redraw the figure that we had. And I had a much better way of showing it, I think, than before. How did I show it? Yeah, all right. So this is the control surface. This is the control volume. Very simply, we'll write V1 and V2. And I'll put a coordinate system on this. And this would be X and this would be Z. And all I want to do is write out the terms in terms of momentum. And velocity. So in terms of this diagram, what are those going to be? Mass flow rate is into the system, so this velocity would be negative. Mass flow rate's out of the system, so this mass flow rate would be positive, because it's the V dot N times rho A is this term. But in terms of velocity, velocity 1 is in the Cartesian direction, so this is positive, and this one is also in the positive Cartesian direction. So if you multiply these together, as you need to get here, then you need to be able to be mindful of what those mean. Out of the system for mass flow rates is always positive. The pre-factor acting on this is always in the Cartesian direction. Likewise, the forces would be positive. This would be a positive force. VE. This would be Fx negative. Yeah, you'll get used to it. Just have to be consistent with your coordinate system. So that's basically all we need to do. And so the simple example to try that out and just explore it for a bit is to ask a question, is that if we have an undershot weir, which is the same as the one that comes out of the book, and I'm putting a gate on the bottom, which I'm going to take out at some stage. And this is the flow rate. And it has an upstream water level, which we'll call uppercase H. And at some stage we'll have a downstream water level, which we'll call lowercase h. Then you could ask yourself a question, the forces acting on this gate, are they bigger or smaller if the gate is open or closed? You can figure out what your answer might be to that. And so we could write the expressions for this. So let's not do that yet. So what are the forces acting on that gate going to look like? Green is for pressure distributions, blue is for velocities. It is early. And so, if we want to calculate the magnitudes of the forces acting on this. So I guess we would draw ourselves some kind of control volume. If I do that in gray, then the control volume is something like this. And so I guess I won't complicate matters by putting a negative sign on it. So we can just look at R is going to be equal to, well, actually let's do it maybe in those coordinate systems. R minus R plus F R A equals nothing's flowing through the system, nothing's flowing in or out, no water's coming into the control volume, no water's going out, so the right hand side is equal to 0. And so this would be equal to what? Resultant force is unit weight times the area times the depth of the centroid, which is h over 2. This is hc. Area is equal to, I know I'm scrolling over this, some distance into the page, which would be B. So this would be HB. So R is just equal to unit weight half H, big H squared, B, right? Yeah. Is that homogeneous? So, yep, so length squared, length cubed, kilonewtons per meter cubed, so this is in newtons, and that's what it's equivalent. So the force required to hold it closed is just the force due to the static fluid. So now we take away the gate. We change our control volume maybe to be something a little fancier. Maybe the control volume should be this. And so what else do we have going on here? If we do the fluid flow in the system in blue, so there's some fluid coming out of here. So this would be some velocity. I'm not sure, I'm going to call it V lowercase h. And there should be some velocity up here, which I guess I should draw just inside the control volume doing this. And so this would be V uppercase H. This doesn't change, but actually what there is here also now is there's going to be a force which I'll imagine the control volume is out here. And this force is here. So this is FH. And this is F lowercase h. And so this would actually be also uppercase H, just for that. So let's do the same thing. So we can keep me on my toes, so make sure I don't screw this up. So let's do the forces. So minus R is acting, plus F uppercase H minus F lowercase h is equal to the velocity h times mass flow rate h plus the velocity lowercase h times the mass flow rate lowercase h. Each of these terms are going to be a velocity in or out of the volume times a density times an area. And so if we expand those, I guess we have something like the reaction plus force in the horizontal direction. We've already got it. It's going to be a half unit weight of water times h squared b. We're going to have this acting in the opposite direction. So just by permutation of this, it's going to be the same. The centroid is going to be halfway down, so it's half height. So it's just going to be the same term, but we'll substitute lowercase h. And that is equal to the velocity. And let's write these terms out. So we'll have a velocity VH times a normal to the boundary velocity. How am I going to do that? Let's just do it as a mass flow rate, which would be a velocity times a density times an area. The area will be uppercase H times B. And we'll add to that the value for some coefficient, velocity, mass flow rate, which is a velocity, times density times lowercase h times b. So all that we need to do is figure out exactly what these components should be. This is the mass flow rate in or out. It's going into the volume, so this should be negative. This is the Cartesian velocity, which we didn't draw in there. But this is velocity x, positive. This is velocity z, positive. So this is b, positive. This would be the mass flow rate, which is a dot product. This term here is out of the control volume. So is the unit outward normal. So this would be positive because it's out. And this would be positive because it's in the velocity of the direction of the coordinate system. So hopefully that makes sense. And so, if we wanted to get from that, I'll take the r over to the other side, and so this will be equal to, I'm just going to move this over here because that solves the sign problem. Not very good with signs. So I'm going to keep, this is going to be a half gamma b, I suppose, h squared minus h squared, I think. This is a negative, so this would be a positive if I bring it to the other side. So plus v uppercase h squared rho hb. This is a positive positive, taking it to the left hand side, so this is a negative. So this would be h squared rho lowercase h b is equal to rx. Does that look right? No. Let's see if it makes sense. Before, r was equal to r was just equal to this term here. So this is the static case. So by opening the floodgates, what we've done is we've reduced the static force that's acting on this because it's being allowed to flow out of here. We are increasing it slightly because there's this term here, which is the velocity term, bless you, coming into the top side. And we're again reducing it because we've got water flowing out. We've got momentum flux, if you like, coming out of the bottom. In the limit, if h is much bigger than h, so if this is a tall dam and it's only a very small piece coming out, then by definition, this velocity here is almost zero, right? Because we can write rho h v is equal to rho h v h, right? So if this goes to a big number, then this goes to be a small number to compensate, right? So just from continuity. So from this, we know that in the limit, this term will approach zero, maybe, and this will be subtracted. So the net result is that if we allow flow out of underneath this gate, compared to the case when it's closed, in which case this is the magnitude of the reaction that we have to apply. The reaction we have to apply, if it's open, is reduced by a static triangular distribution pushing against it, and also the momentum flux, if you like, that's coming out of here, which is given by the mass flow rate multiplied by velocity, which is momentum. Mass flow rate times the velocity you could think of as a momentum flux. Flux is just a velocity. That's it. I didn't, so yeah, so if you want to check this out, the exact same example is given here, and there's some things about the sign convention. We just have to be aware of the sign convention. So this is just the same solution. So what we're going to do is we're going to realize that our basic equation is just this. We've written it slightly differently. We wrote it as sum of the forces are equal to a velocity times a mass flow rate. And we just have to remember that these represent forces in the x, in the y, and in the z directions. And it's equal to velocities in the x, in the y, and the z directions times mass flow rates. And so all we've done this time is we just took one equation. We only need one equation. We could also solve for forces vertically if we wanted to. I'm not sure what it would tell us, but if you wanted to, we could do it in z, and we wanted to, we could do it in x. I think the sum of the forces in both z and x would be zero. No net forces, because the same, yeah, if you took a box, which was this L-shaped box, and you looked at the static pressure distributions on either side, they balance each other in the y direction. And I suppose if you did it in the vertical direction, you'd just end up with a pressure acting on this bottom, which is equal to the height of water above it. And it would have, no, it's not static anymore, so we can't go horizontally and say that we have the same pressure. So, but we'd end up with some distribution. So that's it. So we'll next time we will follow that to do some more examples of flows going around pipes and holding things in place. And next time, I guess the other more interesting thing that we can do, and we will do, is that we'll look at the idea of what we looked at today. So we looked at a Pelton wheel. We took Bernoulli, and we said that if it's moving at some control velocity, control system velocity, then there are two end-member conditions. Static vane has a maximum force. Force with zero, a vane with zero force on it has to be moving at the velocity of the water. And we can use that, the same idea of what we've looked at now, to be able to write the equations in terms of Newton's second law, but now the velocities that we're interested in looking at are the relative to the vane velocities, which is why we're interested in the Fire Department of New York fireboat and looking at the velocities coming out of it and coming into it. Everything has to be in the right reference frame. So we'll do that next time. So next time we'll do a more sophisticated version of the moving vane, and then on Friday we'll talk about lawn sprinklers and Pelton wheels when they actually do go around a circle instead of having that circle being of infinite radius. It's just what we're doing right now horizontally. Okay, great. Welcome back for the week. Questions?